Hello all. This is our first online lecture for Trigonometry, Math 1230. Let me title this. So we have Trigonometry, Math 1230. Let's call this Lesson 1. This is something that's going to require me getting a little accustomed to. This is not the format that I usually deal with. So let's look at the following. You know, we have certain identities, such as the sine squared of theta plus the cosine squared of theta is equal to 1. And this is just the trig version of the Pythagorean theorem. For us, what's important is the fact that this equation holds true for all values of theta. So this is true for all values of theta. For instance, if I had theta equal to, let's say, 1.2, then I have the sine squared of 1.2 plus the cosine squared of 1.2. That's certainly equal to 1. And an equation where the equation happens to be true for all values of, say, a particular variable, in this case theta, this is called an identity. Another example of an identity that I think you know is the cosine squared of theta is equal to, 1 plus the cosine of 2 theta divided by 2. And this is going to be one of the trig identities that's going to be important to you when you study Calculus 2. Now, there are other types of equations. Let's just take a simple one. 2 times the sine of theta minus 1 is equal to 0. Okay? Now, this is certainly not true for all values of theta. What we want to do, we want to figure out what values of theta actually solve this equation. So we want to find those values of theta such that this equation is satisfied. Oops. All right. Well, I'm going to rewrite this equation as follows. This equation is certainly equivalent to saying that 2 times the sine of theta is equal to 1, which is also the same, it's equivalent, and that's what this symbol here means, it's equivalent to the sine of theta is equal to 1/2. So we're looking for all those values of theta such that the sine of theta is equal to 1/2. One way of thinking about this is as follows. I can think of the graph of the sine function. So let's see if we can graph that. This is my theta axis. I'm going to call this my y-axis. And the equation that I'm graphing is y is equal to the sine of theta. We know what that looks like. That kind of looks like this. Here. Oops. My drawings aren't the best. Like that. And so this is 0. Theta equals 0. This is where theta is equal to pi over 2. Here this is pi. This would be 3 pi over 2. Here's 2 pi. And over here, minus pi over 2, minus pi, and so on. And this value, this is certainly 1. Down here, this is -1, right? Because the amplitude of the sine function is 1. And the equation that we're trying to solve up here this equation, we can think of this as locating all those points on the graph of the sine function where the line y equals minus, see if I can squeeze this in here, y equal 1/2, this line, let's say it's going to be here. We're looking for all these points where the line y equal 1/2 intersects the graph of the sine function. Well, if you're like me, you forget what angle has a sine equal to 1/2. But the thing is, I remember how to figure this out. And what we do is we take an equilateral triangle. So all these sides are 1. All the angles are equal. They're all equal to pi divided by 3 radians, right? So this is in radians, and we know that this is equal to 60 degrees. And I divide my triangle in half. And when I do that, this line here is at a right angle to the base of the triangle. So this angle down here, this is a right angle. That means this angle up here is going to be pi divided by 6, which is 30 degrees. Okay? And since we divided this triangle in half, that means that the length of the side from here to here, between these 2 points, this is 1/2. And by the Pythagorean theorem, this side has length the square root of 3 divided by 2. So far, so good? Okay. So now, we know that if I have an angle theta, and theta happens to be an angle of a right triangle, that the sine of theta is equal to the length of the opposite side over the hypotenuse. And if we look at our equilateral triangle up here, then we can see that the sine of pi divided by 6, this is equal to 1/2. So far, so good? Okay. So that means this point here, this point of intersection of the line y equal 1/2 with the sine curve, this occurs when theta is equal to pi divided by 6. Now, we know that the sine function happens to have period 2 pi. It keeps on repeating itself every 2 pi units. And that means that the distance between this point here and this point over here, that distance happens to be 2 pi. Okay. And I can say the same thing here. The distance between this point and this point here, that's also 2 pi. And it keeps on repeating that way. So now what I know is the following. I know that if theta is equal to pi divided by 6 plus any multiple, any integer multiple of 2 pi, this is going to be a solution to my equation. So where k is any integer, these values of theta are solutions to the equation. And the equation that we were looking at was certainly the equation, the sine of theta is equal to 1/2. Okay, but let's go back. So we go back to our graph, and we see that there are some points that we missed. In particular, this point here and this point over here. So I have to find the value of theta at these points, here and here. So let's see what we can do with that. Remember, so a lot of this is recalling some of the things that you studied before. If we have a unit, that doesn't look so good. This is supposed to be a unit circle. This is my x-axis, here's my y-axis. And if I have an angle, let's call it alpha here, like the Greek letters for our angles. And this point of intersection of this radial line with the circle happens to be x comma y, then we know what the sine of alpha is equal to y, and the cosine of alpha, we'll just write this down, we don't really need that, but is equal to x. Good thing to recall. All right, so now what we're looking for now is another angle whose sine happens to be equal to y. And if I look, here's my y value, oops. So if I look at this angle here, this angle, that angle, let me call it beta, oops, beta, that angle also has a sine which is equal to y. All right, so let's use this. Let's use this information. Here we have theta equal to pi over 6. This has a sine which is equal to 1/2. So if I think of this on the unit circle, here's my angle. This is pi over 6. Here's my unit circle, or ellipse. All right, and what I'm looking for is this angle over here, this angle. And again, I'm going to call this beta, only this time beta is equal to pi minus pi divided by 6, which is equal to 5 pi over 6. All right, so now that's another angle whose sine happens to be 1/2. Got it? Again, this is the x-axis and this is the y-axis. And I have to learn how to draw a little bit better using this iPad. This angle here is pi over 6. And this angle here is pi minus pi divided by 6, which is equal to 5 pi divided by 6. Now, let's go back again. Whoops, wrong way. Back here. So this angle at this point of intersection is theta equal to 5 pi over 6. We know the sine function happens to have period 2 pi, which means that this point of intersection, oops, I think I did that wrong when I initially did this. I'm sorry. My goodness, what did I do? Yeah, so this here, this distance from here to here, this is 2 pi, sorry. So this distance happens to be 2 pi. Wonder if I can change the color on this. I don't know how to do that. I'm gonna try something here just to experiment. Oops, it's not working so well. I thought that would change color, but it doesn't. All right. So it's this point here, which is 2 pi away from this point here, is 2 pi away from this point over here. All right. So that means what? That means that this point as the value 5 pi divided by 6 minus 2 pi. This is getting a little crowded there. Hopefully you got the idea. Let's see. So we're going to come back down here. So we have when theta is equal to 5 pi over 6. When theta is equal to 5 pi over 6, we know that the sine of 5 pi over 6 is equal to 1/2, which is what we want. And we know that any integer multiple of 2 pi plus 5 pi over 6, this is also going to have the sine. Its sine is going to equal 1/2. And here again, k is any integer. So k might be minus 1/2, minus 2, sorry, minus 1, 0, 1, 2, 3, and so on. So what do we find? The solutions to the equation 2 times the sine of theta minus 1 equals 0 are the following values of theta. So these are the following. Theta equal to pi over 6 plus 2 pi times k, or any value of theta of the form 5 pi over 6 plus 2 pi k. All right, so we have infinitely many solutions. To our equation. An example, let's just play with this a little bit. If k is equal to 1, we find that theta is equal to pi over 6 plus 2 pi. So this is equal to, let's see, this is 12 pi over 6, so this is 13 pi over 6. And then we also have the solution, theta is equal to 5 pi over 6 plus 2 pi. And this is equal to 12, this is 17 pi divided by 6. Okay, and of course, these are in radians. All right. All right, if you have questions on this, go to the bulletin board, the discussion board, and post your questions, and hopefully you'll get an answer. I have a problem for you to work on. Suppose you're looking to solve this equation. Here, I'll even simplify it somewhat. The cosine of theta is equal to minus the square root of 2 divided by 2. Find all solutions. All right. So just as in the previous case, you're going to find, I hope, that there are infinitely many solutions. And don't forget, this is all in section 7.4 of our textbook, Stewart textbook. And if you look in the syllabus, you should have actually a modified syllabus now. You'll see suggested problems. So look over the suggested problems. And also, check out version or lesson, let's call it lesson 2 of this lecture on trigonometry. All right, that's it for now. Bye.